starting the podcast at the center. Again, so welcome to the center. Thanks for joining us. All right. You're gonna get a clap. Next week, there's nothing. That's the best announcement I could have made. It's the end of the semester, so we are almost done. We have a talk on Friday, however, by a former fellow who is joining us here at the center, Armin Schulz, who will be talking about agency and the case for an eliminative pluralism. So the talk is at noon, as usual. Armin will be here on Thursday in case you're interested in meeting him. And then we'll take a break for a few weeks. So first talk next semester will be given by Sandy Mitchell on January 16th. For those online, the center is still accepting applications for the visiting fellowship and the postdoctoral position until December 8th. So if you plan to submit an application, please do not miss this deadline. Today, it's my pleasure to introduce Lucy Mason, who is a postdoctoral fellow here at the University of Pittsburgh. She's working with Professor David Wallace here. She's a philosopher of physics. Previously, she was a postdoctoral fellow also at the Royal Holloway University of London, working on measurement and in the context of quantum gravity. And before, she was doing her postdoctoral PhD at King's with someone who is also connected to the center, Eleanor Knox, because Eleanor was a senior visiting fellow a couple of years ago. You never escape orbit of the center. Somehow that's what makes it a center. All right. She has published in the philosophy of physics. I will mention her article Foundations of Physics, Perspectives on the Quantum State in 2025. And she has a number of manuscripts that you can find on the Pitt archive field side. Today, Lucy will be talking about methodological intersubjectivity. The floor is yours.
Great. Thank you for being here and thank you for having me. It's very nice to be here, especially as I'm based here for at least this year and possibly next year. And so it's really nice to kind of share my work with everyone, hopefully get some feedback on it as well. So the project I've been working on is about intersubjectivity. So this is something that's become quite an issue in some of the interpretations of quantum mechanics, which is why I was working previously. And I was interested in kind of generalizing this a bit more. So this talk is kind of largely aimed at a kind of general philosophy of science audience, kind of, but using examples from philosophy of physics, with some philosophy of physics at the end as well, which is kind of showing why I'm interested in this topic and how it applies to philosophy of physics. So with that, as I have two aims. So the first is this general philosophy of science goal, which is to create a definition of what I'm going to call methodological intersubjectivity, and examine how it's going to be applied in the case study of time measurements that we use kind of globally and how that relates to kind of relativity theory and the use of that in these time measurements. So basically what I'm going to be looking at is the way that methodological practices like calibration, measurement techniques, standardization of units and things like that create a form of intersubjectivity in science that's a really important foundation to how we have robust and reliable scientific knowledge and how that knowledge is shared between multiple perspectives or multiple agents. The second aim is a more specific one, which is for philosophy of physics. So as I said, there's been these debates in philosophy of physics, particularly quantum mechanics, about intersubjectivity and whether or not perspectival interpretations of quantum physics can achieve intersubjectivity. And some of them have been making use of things which I will say fall under what I'm going to call methodological intersubjectivity. And I think it would be very useful for them to have a definition that's clear and usable and showing how it relates to kind of other forms of intersubjectivity. So that's the kind of more specific debate. But most of the talk will be taken up by just presenting the definition and explaining how it would work, how it would function, before looking at how it would be used in this specific debate. So the motivations for doing this are kind of also twofold. So the first is the general philosophy of science aim is that intersubjectivity and scientific knowledge is obviously incredibly important in understanding how it is we have robust knowledge of science and how we have agreement between agents come to be developed over the period of kind of scientific progress. And there has been quite a lot of recognition in philosophy of science, incredibly recently, of how much measurement can be subjective and how much it can rely on really circumstantial aspects of what makes a measurement work. So, for example, I was reading about kind of the Stern-Gerlach apparatus in physics, which is first used to measure atomic spin, and how, the early experiments of that only seem to work when the experimenter was kind of really looking closely, and it turned out that he was, it was the tobacco on his breath that was making the experiment work. And there's a lot of kind of unrecognized parts of measurement which rely on things like this, where it's really, really specific. It prevents kind of reproducibility, and it kind of, in some cases, is taken to slightly undermine the kind of the status of scientific evidence, in the sense that the measurement you make is so highly specific and dependent on subjective or circumstantial elements that it does seem to be a challenge to that being counted as objective scientific knowledge that can be shared by a whole community. There's also been a lot of focus on values in measurement, so how the development of measurement techniques and definitions of measurable properties, as well as scientific paradigms as a whole, can be massively influenced by the values you go in with, what we're trying to prove, and this can massively affect measurement again. And this also undermines kind of the status of measurement. And finally, in a kind of wider sense, the recognition that a lot of knowledge is really relative to a particular perspective. Normally, a scientific framework, measurements are often heavily theory-laden and can be very specifically understood within a narrow framework. And if you don't buy into that framework, it kind of undermines the interpretation of the measurement results. So all of these things kind of focus on the ways in which measurements can be highly perspectival or subjective. So I think it's really important to have a clear sense of how it is that we overcome those difficulties and create scientific knowledge that is robust and shareable and has a firm basis that we all have intersubjective agreement on. The second kind of motivation is the specific philosophy of physics debates that I've been working in. So the problem of intersubjectivity has turned up originally in quantum mechanics. It's then being kind of generalized to other domains as well and become a question of whether or not a theory in physics, a model of the world in physics, should be able to model its own empirical confirmation. So whether it can model the own conditions for its own discovery. So this can be quite minimal in the sense of just explaining what observables of the theory are and how they could be measured, to kind of more in-depth models of how an observer fits into those physical theories. There are some already existing ideas about methodological intersubjectivity being used in that, but they're not incredibly precise. And one of the big questions in this is whether or not methodological intersubjectivity depends on intersubjectivity given by the theory in physics itself. So links between perspectives or observables within the theory. And that's kind of one of the questions I'm going to try and look at today and kind of schematize how we might go about answering that question. And the answer is just going to be that it's really complicated, and that actually it's been underappreciated how complicated that is, and a lot more work actually needs to go into developing an answer to this question that would allow us to kind of move forward to this debate and get clearer on what it is that we're actually trying to answer. Okay, so I'm now going to go a bit deeper into each of these two areas to talk about exactly what kind of resources I'm drawing from. So the general philosophy of science side, what I found really useful in this is Michaela Massimi's perspectival realism work. So she's been looking a lot at how we can have a form of scientific realism that takes into account how much scientific knowledge is relativized to a particular perspectives. And she defines perspectives as socially and historically situated communities. So this covers, a group of scientists working on a particular theory, but she also wants to kind of expand the idea of science to cover kind of people who are making measuring devices, which includes both scientific expertise, but also expertise in sort of craftsmanship and the kind of engineering and the kind of production of basic materials like glassware or things like that that are involved in making measurement devices. And often kind of she makes a point of saying that this often relies on kind of craft communities that are very far outside the traditional scientific paradigm and which deserve kind of recognition for the input they have to scientific work. So this kind of definition of perspective is very broad, very general, and really focuses on kind of frameworks of knowledge and kind of accepted norms within a group. And she has two useful ideas for talking about how perspectives of these kinds can be related to each other and how you can have knowledge shared between them and some kind of intersubjectivity created. And she's saying that they basically rely not on direct agreement about measurement results or on the theory that they're using, but often what's creating intersubjectivity is epistemic methodological principles. I'm going to be focused on the more methodological ones. The epistemic principles look more at kind of shared ideas about things like causation or causal reasoning in science and things like that. Methodological is what I'm going to be focusing on, is particularly these mechanisms of calibration and things like that. So the two notions she kind of defines, the first is called intersecting. So different perspectives share some kind of principle that allow their results and data to be compared and combined. So this can mean that you can have very different measurements being performed by different communities, but they recognize that they're both trying to measure the same thing, or that they're using some kind of shared standard that allows us to transfer our results from one to another. So she uses examples of things like how we combine data from boreholes in ice with tree rings to get a history of the Earth's temperature. So two different measurement techniques, but are both focused on the same phenomena of temperature and using enough similar methods that we can show that these are compatible and are giving us robust knowledge about the shared phenomena, even though both perspectives are using very different theories to produce this measurement result. So the second is called interlacing. So this focuses on much more kind of material exchanges of knowledge between perspectives. So where two perspectives come together and sort of exchange measurement techniques, or you have the kind of historical lineage of the development of a measurement technique or the development of some aspect of the theory. That means it's kind of passed through various different perspectives. And that creates a kind of shared knowledge between all of them, where because of the shared history, they're all focused and using the same standards for what this thing is. And that creates a kind of way in which we can share knowledge and links together what might at first seem like quite different perspectives. So that's the kind of general philosophy science stuff. I'm going to be drawing on intersecting and interlacing quite a bit. The other is the quantum mechanics stuff, the philosophy of physics. And the first thing to know is that this is using a very different notion of perspective. So there are some interpretations of quantum mechanics that focus on things like community perspectives in maybe a way that's similar to Masami. But generally, they're talking about individual agents in quantum mechanics. So none of the kind of shared group ideas, but a single agent performing a single measurement. And debates in quantum mechanics sort of started with Wigner's friend paradox, which is a very particular paradox within quantum mechanics, focusing on two agents isolated from each other. One performs a measurement and gets a determinate result. The other revolves the system, trying to work out what's happening with his friend, and uses unitary quantum mechanics to get a superposition of two results. And the question is there these two agents disagree on what's happened in the scenario? Is one of them right? Is one of them simply an epistemic prediction, or is it also ontological? And this kind of problem has been generalized into a general question of, can two agents get to the same result at all? So in this kind of scenario that I've drawn, you just have two agents in a lab, both looking at the same measuring device. And it seems like quantum mechanics, or at least particular interpretations of it, struggle to explain whether or not we can guarantee that both Alice and Bob actually see the same result. It's possible within some interpretations of quantum mechanics that Alice could be seeing spin up on the spin measurement and Bob could be seeing spin down. There's nothing to guarantee that they get the same result. And this is based on the measurement problem and the kind of probabilistic collapse of the wave function. So I'm not going to go super deep into the technical details of all of this, although you're obviously very welcome to ask me about it. But I kind of wanted to set up that that's where the problem has come from, and that it's focused very much on individual agents as opposed to kind of group inferences. And as I said, this is particularly a problem for perspectival interpretations. So some interpretations like Everettian or Bowman mechanics or dynamic collapse often rely on some form of decoherence to solve this problem. Perspectival interpretations struggle to do that. Because they're very localized to individual agents, they often struggle to model the kind of decoherence spreading between multiple agents. And a lot of work's been done on this, particularly by Emily Adlam, who's basically challenged these theories and said that all perspectival theories must have some kind of what she calls cross-perspective links that establish a link between your two perspectives. And I'm going to generally call this theoretical intersubjectivity. So it's intersubjectivity provided by an element of the theory itself. And Adlam very strongly argues that any perspectival theory needs to have this. And the kind of paradigm example of a theory that does have this is general relativity, or relativity as a whole. So general relativity uses reference frames, and I'll talk more about in what sense that could be seen as perspectival later. But it also has a very coordinate independent approach, and we have very clear transformations between reference frames. So it's seen as an example of a theory where you have theoretical intersubjectivity without any problems. And the idea is that quantum mechanics should live up to this standard. And the motivation for this, as Adlam puts it, is about empirical confirmation. So an interpretation of quantum mechanics must be able to tell a story about how empirical confirmation works in the context of quantum mechanical experiments. And the idea is that empirical confirmation requires that I can share my measurement results with another agent. I must be able to guarantee that we're both seeing the same result, otherwise I can't trust scientific data. And so without a firm mechanism of intersubjectivity, there's no way that we could have discovered quantum mechanics, or though at least we would have no epistemic justification for believing in quantum mechanics, which is obviously a problem. We do believe in quantum mechanics, so that seems like the interpretation is failing to explain a very basic fact about the theory. And this isn't specific to Adlam. I think there has been other work by people like Eric Curiel on talking about how every theory in physics must be able to schematize the observer in some minimal way. It doesn't have to be a full model of the observer, but it has to have something to explain how your theory connects to empirical data. And as I said, it's largely focused on perspectival interpretations, but it's not limited to that. That's just been where the focus of a lot of this debate has been. So another example is the quantum Darwinism program, which is part of quantum decoherence and is focused more on the general measurement problem. And Zurich, who's the kind of proponent of this debate, also talks quite a lot about intersubjectivity and the idea that two agents need to be able to independently verify a quantum measurement result. So one particular interpretation that I'm going to mention is cubism. So this is a particular interpretation, it's a perspectival interpretation, and it's based on interpreting quantum mechanics through decision theory and sees the quantum formalism as a kind of normative guide to an agent's predictions and actions. So it's quite a radical interpretation, it's very subjectivist. They're using personalist probabilities where I assign a quantum state to a system based on my beliefs and knowledge, and I act on my beliefs that are laid out in that quantum state to make predictions. I update that with new information coming in. It's not a purely epistemic theory. They do think that this mechanism is all there is to science. This is constitutive of what the world is this interaction that I have with it in terms of actions and beliefs and predictions. And that no purely objective third-person model of the world is possible at all. All this is all we have. And because it's so radically personalist, they've had a lot of problems with intersubjectivity. So there's been a whole bunch of papers challenging this. I've also just been writing a paper kind of looking at their solution. I'm very interested in it. I don't agree with the theory as a whole, but I think it raises a lot of interesting questions. And one of them is about methodological intersubjectivity. So the solution that the cubists have to situations like this, so they're looking at situations of how can I guarantee two observers have the same measurement results. They're drawing on a lot of questions that are similar to philosophy of science, looking at the really subjective elements of measurement, how much it can be circumstantial, how much it depends on a particular agent's choices and actions and beliefs about the system. And they're also drawing a lot on phenomenology, so things like Husserl and Merleau-Ponty, talking about how measuring devices are kind of an extension of the human body and our senses. And this is where a lot of kind of Emily Adlam's criticisms about theoretical intersubjectivity are aimed at, is this kind of cubist view. So what they're saying about intersubjectivity is that they're basing it on an account on the philosophy of metrology. So this is from Jacques Spinard, who's been writing about this recently, explicitly stating that they are relying on metrology for this. And this quote from Jacques in a paper last year is saying that in a situation like this, how do you know these two agents are agreeing with each other? Well, he says that in practice, if you're Alice, all you can really talk about is whether or not you expect Bob to agree with you. And to establish that, you talk to Bob, you examine the measuring device, how he set it up, how he's interpreting it, how he's using it, whether or not he has sufficient experimental expertise. And you make your judgment about whether or not you expect Bob's result to agree with yours based on whether or not you think he's good enough at performing the measurement. So it is relying, again, on these principles about the methodology and the metrology of the situation rather than something within quantum mechanics itself. So this is basically what methodological intersubjectivity is. That's how I'm going to define it. And I think that giving a clear definition would really help in situations like this. Okay, so that's the kind of motivations and the kind of what I'm drawing from for this definition. So I will now turn to the actual definition. So I'm defining methodological intersubjectivity as 1, the coordination of perspectives, and 2, the creation of shared perspectives through practices such as the standardization of units and the continual process of calibration and comparison, the defining of measurable properties, and the establishment of robust measurement techniques. So this definition is very inspired by Michaela Massimi's sort of definitions of perspectives and some of the things she talks about. And I'm going to be kind of drawing on a lot of her resources to kind of spell out what all of this means. And I'm basically just going to talk you through this definition by applying it to a case study and showing it how it applies in a practical situation. So the case study is going to be relativistic time measurements. So we live in a world governed by general relativity, where time is understood to be a local phenomena which passes at different rates depending on the gravitational field you're in. And that makes time measurements very difficult in a lot of ways because it's essentially localized to a particular clock. And yet time is also something we rely on very widely to coordinate our day-to-day needs. It's the basis of a huge number of scientific measurements. So it's really important that we have intersubjectivity when it comes to time measurements, and it's a particular challenge. So I think it's a good case study. It's also one that avoids the particular problems of quantum mechanics. And because relativity theory is often seen as the theory that has theoretical intersubjectivity really well, it's got transformations between reference frames well established, it makes a nice contrast of saying, well, if we do have theoretical intersubjectivity, how does that relate to methodological intersubjectivity? And then we can apply the lessons to quantum mechanics once we have a better understanding of what's going on. So just before I get started, I want to kind of quickly talk through how we might understand relativity as a perspectival theory. The first is in Michaela Massimi's sense, so we can talk about the communities involved in its discovery. There have been different interpretations of the theory, but this is largely historic, and I'm going to talk a little bit about that. We tend to interpret it pretty unified now. The other sense of perspectival is this kind of more philosophy of physics sense, which is that it's physically perspectival in the sense that we use reference frames. So a reference frame is going to be saying, I could be the origin and the basis of my reference frame. I use that to define my coordinate system, where my origin is, what state of motion my reference frame is. That tells me whether my reference frame is inertial. And that's very important for a lot of relativity. As I said, you can formulate a coordinate independent general relativity, and that's very important to the theory as well. But reference frames are also very important. David has a very nice paper explaining why it's not a bad thing to have a reference frame-based interpretation. The other sense of perspectivalism that could be brought into relativity theory is some discussions about how all observables in relativity are relational. So general relativity does not predict the values of the position or time of any particular things. It predicts functions of two variables together. So I could predict position as a function of time. Time is normally the independent variable in this scenario, but it's not the only one. But general relativity will give you a prediction of the dynamics of that relational observable. If I ever want to produce a measurement outcome, I need to situate myself in a reference frame that fixes the independent variable. And that will allow me to get a measurement result for my dependent variable. General relativity will not on its own make that prediction for me. It requires additional information about the reference frame to do. So that's another sense in which perspectivalism has been discussed. Okay, so that's relativity and the ways in which it's perspectival. Back to the case study and methodological intersubjectivity. So the first part of the definition is about the coordination of perspectives. So one of the most important mechanisms of coordinating perspectives is the definition of a standard unit that all perspectives will use. So in the case of time measurements, the second is defined by taking the fixed numerical value of the cesium frequency, which is the ground state hyperfine transition frequency of a cesium atom, particular isotope, and that will cause a particular frequency, will cause the electron to jump energy levels. And we define that by definition as this very long number, which is the number is chosen so as to be equal to our previous definitions of the second. And we fix that number. That is written into the definition of our unit. And we say that whenever I have a cesium atom, I am assuming that whatever frequency works and creates that transition is that number. So that's how I assign that number to a physical phenomena in the world and use that as a basis for the definition of the unit. And this definition is maintained by the BIPM, so the International Bureau of Weights and Measures. The acronym comes from the French, which I'm not going to try and pronounce. So they have an international authority which gives them license to set these definitions and to maintain this as a standard. So the most important way in which this creates intersubjectivity is simply that every clock I have is taken to instantiate this definition of the second. And this is an example of Massimi's kind of intersecting, the idea that all of the perspectives have a shared standard that allows us to compare the results. If I take all my clocks to use this standard, that creates a basic intersubjectivity between them, where I can be sure that my definition of the second is the same as yours, and that our measurement results can be directly compared in that way. In practice, instantiation is not so easy. So as I said, the definition relies on fixing a number and saying, when I have a cesium atom clock and I have a frequency of light that's being shone into it, it is that number. In practice, there is variation between different clocks, which is a problem because our definition says they're all the same, but it's idealized in the sense that no actual set of clocks are all going to perfectly instantiate this. So one significant challenge is modeling how well your clock in your individual perspective instantiates this idealized definition, and I can create a model of what approximations I'm making, what parts of this idealization need to be relaxed in the case of my individual clock, and I can model what uncertainties that brings in. So Tal, if you know him, has done some amazing work on spelling out exactly how that happens and the kind of approximations we need to deal with. But one of the big mechanisms is managed by the BIPM, and this is to create a network of clocks that multiply realize the instantiation and together combine to form this idealized realization. So they have this network. So this is the image I've been using as my background, the full version of it. This is the BIPM network of key comparisons. So they do this for not just time, but for all of our standard units, so length and weight as well, and things like that. And how it works is that they have a kind of their core facility. They're based in Paris. They have a number of core measurement facilities, and every nation that signed up, which is most nations, have what's called a National Measurement Institute. Every country has one. You're only allowed one, and that's designated as the official BIPM network hub. And all of these different institutions maintain their own clocks. The BIPM takes the results from all these clocks, averages them into a network, comparing the results, correcting for various effects, modeling the uncertainties, and creates this vast network that allows us to kind of average out all of the different imperfections in the clocks to instantiate the idealized definition. And the time that they maintain as this idealized instantiation of the second is called international atomic time. There's various time standards that they kind of go through. Again, Tal has some work kind of spelling out all of the different steps that go into creating international atomic time. But it's taken to kind of be what this network is designed to instantiate. And for the case of time, so this diagram says they have, I think, 810 key comparisons. That's for all units. For time specifically, we have 16 primary standards, which are really, really accurate cesium atom clocks, which are designed to be incredibly precise about the time measurements that they make. These clocks, however, are not great for long-term stability. You can run them for kind of a period, I think it's about 5 weeks or so, before they start to become less accurate. So we also have about 450 secondary standards, which are different types of clocks aimed at long-term stability. And the BIPM does a lot of work combining all of the different results to create a time standard that is consistently accurate over long periods of time. So one function of this is to realize the idealized definition of the second. The other is to provide a mechanism of calibration. So rather than look at each individual clock in a perspective and independently model how well it instantiates the definition, we also rely on a mechanism of calibration and traceability back to this primary network of standards. So this I'm going to propose we can understand as a form of Massamy's interlacing. I am talking about slightly different forms of perspectives here. I'm talking about individual time measurements rather than communities. So it's slightly changing the definition of interlacing, but I think it maintains this idea of there being a traceability between an individual perspective calibrated and traced back to a whole network of intersubjectively shared standards of the instantiation of the second in a way that ensures that if you have a laboratory measurement using a time standard, that it will meet the international standards of rigor in precision. So to make this point a bit more, I'm going to look at some actual examples of clocks. So first clock I want to look at is this 507.1b, sorry, primary time and frequency standard. So this is, I think it's a cesium atom clock. It might be a rubidium atom clock. It's created by this microchip brand. They make apparently a lot of the most accurate timekeeping devices we have. And it comes as this modular form. So you can buy this off the shelf. They're very expensive, but you can buy them off the shelf. And this is from their brochure online, which is talking about laying out exactly what this measurement device offers you. And they explicitly talk about how one of the kind of major selling points is that any one of these devices is explicitly calibrated to the BIPM's network. So in this case, it's calibrated, this is a US brand, so it's calibrated via NIST, which is the National Institute of Science and Technology, which is the US's national measurement institute that participates in the BIPM. So any device they make will be calibrated against that laboratory, and you can trace that calibration back. And the modularity is really important in this, in the sense that all of that work is done in the manufacturer stage. By the time it gets to an individual laboratory, they're going to perform local calibrations depending on exactly what they want to do. But most of the work is done prior to it ever even arriving at the laboratory. Another example is the Sync server. So this is the same brand. This is a slightly different kind of clock, which is specifically targeted at synchronizing time measurements across distances. And again, these are derived from the same standard. And the reason I want to look at this one as well is that it brings in the use of GPS. So GPS is what they use to synchronize time measurements across distances. And GPS is really interesting. And this helps us understand how relativity theory is being used in these measurements. So the GPS, the Global Positioning Service, is based on the principle of the constancy of the speed of light. So I have my speed equals distance over time equation. If I take the speed of light, which is the signals GPS is sending, to be constant, then I can work out this equation up here. And how this works is that if I'm standing here, I have unknown time and position coordinates. Somewhere in the sky above us, at all times, there will be 4 GPS satellites in view. And those will be sending signals to me. And if I instantaneously receive 4 signals from 4 satellites, and those signals tell me the coordinates, exact coordinates of the GPS satellite, I can create a system of 4 equations that allows me to solve for my time and position. And this is very, very precise. So if I get the signal of the clock and it's telling me where it is, but if it gets it wrong by even a nanosecond, it can tell me I'm 50 meters away from where I actually am. So this is very, very sensitive to exact precision time measurements. So it's really important that we use precision time measurements. So all of these satellites have these atomic clocks on them. The other important thing that GPS has to deal with is corrections for relativistic effects. So we are in a very complicated frame of reference where on the Earth, we mainly assume that everyone's stationary on the Earth. If you're driving in a car, probably isn't going to make enough of a difference. But satellites are obviously very high up. They're rotating at a different rate. And we have to correct for the kind of relativistic effects on the satellite. So one of these is just the rotation of the Earth, which causes a kind of interference effect known as the Sagnac effect. And there's some work spelling out how that depends on the kind of exact reference frames you're using to model this in GR. We also have to account for the gravitational field of the Earth. So the clocks in satellites versus clocks on the ground versus a clock up a mountain are all at different altitudes and therefore at different gravitational potentials. So in GR, we model this by using kind of a weak field approximation of the Einstein field equations, which treats the mass energy tension as pretty much a Newtonian gravitational potential, but allows us to deal with it in relativity. So the effects are small enough that we can do that rather than a full solution. We can ignore the kind of more in-depth gravitational effects from GR as negligible. But it is an important part of correcting for the different altitudes of these clocks and how they're going to relate to each other. And then the last one is the kind of Doppler effect. So as far as I understand it, this is about the kind of light signals as we're sending them through a gravitational field. It essentially causes a kind of gravitational blue shifting of the frequencies, which is going to affect the result we get and we need to correct for. So GPS all does this for you. They have very complicated networks modeling each of these effects and how big of an effect they have, how much we need to correct for it. So that kind of highlights the amount to which relativity theory is really integral to the use of these clocks. And this is also used by the BIPM in maintaining their network. So GPS system itself relies on the definition of time given by the BIPM, but BIPM then uses the GPS system to work out how to synchronize their network of clocks. It's a kind of reciprocal relationship where they kind of pass results in stages. Okay, so one practical use of this in measurement is the Event Horizon technology, Event Horizon telescope, which is the telescope that produced the kind of images of black holes that came out a few years ago, very exciting. And they use what's called very long baseline interferometry, where they basically take two measuring devices at very far apart and look at interference effects and how each one is receiving light signals from space. And from that, they can basically combine the results of these two measuring devices very far apart. They can literally be on other sides of the world to create measurements that are bigger than anything we could construct in one device. And this relies on them being able to synchronize extremely precisely the results they're getting at these two different measurement stations. And so this is from their science page on their website, kind of explaining how to get this precision, you are using atomic clocks at every station in the measurement. And you're also coordinating them via the GPS signal. And from this network, using these kind of methods as a basis, you can create a measurement device that's kind of bigger than anything we could construct. Okay, so that's the kind of coordination of perspectives. Now I want to talk about the creation of shared perspectives. So this is kind of changing gear a bit, taking a more historical turn. I'll come back to more about the kind of calibration stuff later. But a major part of creating a shared perspective and creating intersubjectivity about these results is in clearly defining what we're measuring, how it applies, what it applies to, what's its domains, and what techniques are reliable ways to measure it. So in the case of time, we've been measuring time for so long that this is very standardized now. But I think in a lot of other fields, this is still quite a significant part of creating intersubjectivity, is working on definitional debates and identifying robust measurement techniques, particularly in fields like neuroscience or psychology, social sciences, which are newer science. They're dealing with kind of defining new concepts all the time. And to get these kind of to a point where they can be intersubjectivity shared, you have to say, well, if I'm measuring this thing, this is the way to do it. This is the technique that I can rely on, which is getting at the thing I'm talking about. And this is the kind of domain in which it applies. And this was also, I think, a part of the history of relativity theory, even if it's pretty well established now. So I'm going to point to a few key historical facts that kind of show this. The first is that one of the major results in the development of relativity was the Michelson-Morley experiments performed in the 1880s. And they're often framed as being about the ether theory and disproving the ether theory. the original papers were not really about the ether theory. They were about developing light waves as a standard of measurement. So this is one of the paper, I think it's from 1889 by Michelson and Morley, which is titled On the Feasibility of Establishing a Light Wave as the Ultimate Standard of Length. They were using it for length, not for time as we do now, but that is now the definition we have of length as well. It's related to the wavelength of light defined in the second. So that's the kind of context in which relativity theory was developing. There was this huge pressure to develop really reliable measurement techniques, and that's what they were performing these experiments for. The kind of second fact was carrying on from this. This was part of a much bigger debate about conventionalism in measurement. So Poincaré was a significant figure in relativity theory, talking a lot about whether or not the definitions of measurements were pure conventions or whether they were kind of a more realist interpretation of measurement. The development of measurement theory was also kicking off in the first half of the kind of 1900s. And a lot of key figures, such as Poincaré, who were working in relativity theory, were also sitting on political committees about the standardization of time units and time zones. So there was a very clear connection between the kind of development of relativity and the development of a system of units that can be shared internationally. We also had kind of a lot of early debate and objections to Einstein's particular interpretation of relativity theory. So Lorentz, obviously famously, was the one who actually came up with the Lorentz transformations, which are the transformations between reference frames. But he disagreed with Einstein's formulation. He thought that there was an absolute time wasn't local. He also, I think, had some interaction with Henry Bergson, French philosopher, who had a famous debate with Einstein. He's generally considered to have lost that debate badly. But I think some recent work, including this book by Jimena Canales, has challenged that and said that actually that's based on a misunderstanding of what Bergson's saying. And Bergson was saying basically, the time that's measured by clocks in relativity theory is not necessarily the same as the time that I subjectively experience. So it's a debate about essentially, what is this thing that I'm measuring? What does it apply to? How broadly does it apply? Finally, related to this debate with Bergson was the introduction of Paul Langevin's twin paradox. The twin paradox is now very famous, the idea that I could stay on Earth, my twin gets in a spaceship traveling at the speed of light, goes away and comes back younger than me. This, when it was introduced, was actually quite controversial, because prior to that, there had been no suggestion that relativity theory would apply to biological organisms. It requires an extra step to say, whatever internal time mechanism my body is keeping is sufficiently similar to the clocks and rods in Einstein's theory that the theory will apply. This is now generally accepted. It was not at the time. People like Bergson very strongly rejected this thesis. And the acceptance of that really created what we take to be the interpretation of relativity theory we have today. Okay, that's some of the history. The other way that we construct a shared perspective is not just agreeing on the interpretation and the applicability of the theories, but in a much more literal sense, creating a shared reference frame. So this goes back to the network of time that I was talking about. So we are all in a shared reference frame. It is the time in which we have coordinated universal time, which you will see on all your clocks. This is related to the international atomic time. They have to add in some leap seconds to keep the atomic time in timing with the solar day. Otherwise, they're pretty much the same. And the history of this has also developed over a long time. So time measurement started with basing it on local meridians and maritime navigation. We then introduced the pressures of railway scheduling, so the railway industry, and the need to have time schedules that spanned, the width of continents, created this massive pressure to agree on time zones, so that this caused a lot of logistical problems. We then had radio communication came in, which introduced new challenges in terms of sending signals, and the invention of radio communication devices, again, heavily involved in the physics of relativity and understanding how atmospheric effects affected this kind of communication. These kind of challenges led to the agreement of Greenwich Mean Time in about 1880s. About 1884, I think, is when it was officially declared as the universal meridian. We would count time from Greenwich Mean Time. And from there, we also agreed to count it in whole number intervals. You have to be 1 hour or more offset. And this is the kind of period of this is all of those points where relativistic physicists were sitting on committees to help make this more precise. So Greenwich Mean Time was gradually replaced by UTC to make it defined within relativity theory a precise reference frame rather than relying on the Greenwich meridian. I wanted to point this out because I think it's an excellent example of Masami's idea of interlacing, where the historical lineage of this created a shared perspective, which was contributed to by marine engineers, railway engineers, communications, policy and industry, as well as relativity theory. And all of this massively contributed to the discovery of and development of relativity theory. Okay, so what is the UTC timeframe? So the UTC is relative to what we call terrestrial time, or the terrestrial reference frame, which is based on the Earth's geoid. So the Earth's geoid is the mean sea level of the Earth under its own gravitation and rotation, so ignoring gravitation effects from the moon and things like weather patterns and stuff like that. This is roughly what it looks like. It is very uneven. It massively, we have to very carefully map exactly what the mass distribution of the world is to get that reference frame. This is a very approximate representation of it, which is commonly used within systems like GPS. So systems like GPS, which are relying on International Atomic Time, which is very closely related to UTC, are based around what's called Earth-centered, Earth-fixed coordinate system, where my coordinate system is polar coordinates, spherical coordinates. The center is at the center of the mass of the Earth. And I then use basically longitude and latitude lines to set my coordinates. And I take a kind of roughly spherical, in this case, it's idealized as a perfect sphere. In reality, it's not, obviously. But at that level, at that sphere, we have a constant gravitational potential. And that rotates with the Earth. So it's Earth-centered and Earth-fixed. It's rotating with it. And that's the kind of reference frame we use in all of these kind of GPS systems and by the BIPM and things like that, to base their calculations of gravitational effects and the corrections they need to do of this. And there is, in fact, an entire international organization dedicated to working out precisely what this reference frame is. And the assumption is that every clock we have at rest on Earth runs at the proper time of this coordinate frame. So the idea in general relativity is that your clock in its own frame of reference is what we call proper time. A clock that's moving within my reference frame might run at a different rate. That's why I see time dilation effects. But my own clock in my own reference frame, that's proper time. And we are assuming that every clock at rest on the Earth runs at the proper time of this reference frame. And any corrections we have to do to fit that definition in the calibration networks we do are a sign of an error in that measurement and uncertainty. But the definition of the time on the clock is relative to this reference frame. And it's not the only reference frame used. We have a celestial reference frame for astronomy. We have lots of different approximations of this, slightly different versions that are all useful. But this is a kind of common definition that puts us all within a shared reference frame for our time measurements. Okay, so that was a lot of information about time measurements. So I wanted to kind of draw out what I'm taking from that a little bit. So the first thing is that a massive part of creating the intersubjectivity I'm talking about is the choice of model and how we apply it. So the choice of definition, the choice of the reference frame that I take my measurements to be operating in, the choice of what my measurable phenomena even is. So we can call International Atomic Time a phenomena that I'm aiming at and that I take all of my clocks to be aiming at. And that defines what corrections I'm applying, how I calculate the uncertainties. And that's a kind of choice I make. I could equally take my clock, and in many cases, we do take our clocks to be measuring a much more local version of time that's not relative to this shared coordinate system. And that's the same clock, same mechanism, but I interpret it differently based on what the aim of my measurement is. And that tells me how do I actually make the inferences towards the phenomena I'm getting to. There is a lot of agency in these choices. This is kind of ineliminable in the fact that the agent making this measurement has a huge amount of input in what the result is. And this is why I think a lot of the philosophy of science objections to measurement come from, the way in which we can have extremely subjective elements of measurement or extremely perspective dependent elements of measurement. And the way that we get around that incredible subjective element is by collective agency and decision making. So the international organizations I've been describing set standards that we all use and we all agree to use that make sure that the agency involved in this does not make our measurements so subjective that they're useless to each other. And, you know, time is an area where we have a massive international effort to make this possible. A lot of times in science, you don't have an international organization giving you the reference frame and giving you a calibration network. So it relies much more on local discussions among scientists about conventions. And it's a lot less, it might be a lot less perfect, a lot less well-functioning, but that's the kind of basis of intersubjectivity. And intersubjectivity in one area can benefit other areas as well. So the other reason time is a good case study is that it's the foundation of a lot of measurements around the world and a lot of measurements in other areas. So the kind of reference frames I was talking about with the Earth geoid on the last slide are also incredibly useful for climate science, a detailed model of the Earth, its gravitational field, its mass, the height elevation, water level. And there's also kind of some measurements by, for example, the European Space Agency, which are using atomic clocks to measure the height elevation of the Earth as well. So they're also relying on this very precise timekeeping measurements to produce data that's used across climate science, which is an area we really need intersubjective agreement in, and where it's much more challenging. Okay, so for the last 5 minutes, I'm going to very quickly turn to philosophy of physics. So this definition, I think, can be used across science, but when it comes to particular problems of physics, these are all very hard things to model within physics. We do not tend to model agency and decision-making and the application of models of physics within physics. But when it comes to the question of theoretical intersubjectivity and how methodological intersubjectivity relies on it, we have to kind of face the question of, can I model how I apply physics within my physical theory itself? So there are kind of 3 ways in which these two concepts could be related. So they could be exactly the same as each other, they could be independent of each other, or they could rely on each other in some complex way. The first option, that they are basically the same thing, I don't think anyone really believes. I think it's a straw man position. I think everything I've spoken about shows that to be false. We may use general relativity a lot in methodological intersubjectivity, but it's not all that we use. So moving on to the second option. We could say that methodological intersubjectivity is independent of the intersubjectivity provided by reference frame transformations. This is what cubism is relying on, that these two are independent. They do not need theoretical intersubjectivity. There are some points in their favor from this case study. So the standardization and realizability of units, the definitions of measurable properties, the choice of shared perspectives and reference frames, those are all independent of GR to some extent. There's also agency, because cubism is a theory built around agency. That's not modeled within GR. There's also a lot of points against that position. So as I've shown, the GPS system using gravitational corrections in GR is fundamental to how we calibrate and synchronize time clocks, how we define reference frames, how we apply corrections to actual clocks. So GR is being used a huge amount in these methodological conventions. So there is some work by cubism to show that, unlike relativity theory, quantum mechanics is not extensively used in metrology. And it's not used to synchronize perspectives in the way that relativity is. I think that's an ongoing challenge. I think they're doing some good work on showing that quantum mechanics differs in this way. But there is a deeper problem, which is what people like Emily Adlam are getting at, which is that fundamentally what's different about quantum mechanics to relativity is that quantum mechanics undermines our variability to communicate as agents, and our variability to trust that we perceive the same thing, which relativity theory doesn't have this problem. And all of those things which are independent of relativity theory rely on communication between agents. So that's the kind of major difference that quantum mechanics has to face. And that leads on to the option that they are related, that methodological intersubjectivity does rely on theoretical intersubjectivity, and there's lots of different ways to spell that out. The first is that it's just mere use. So we use coordinate transformations to coordinate perspectives. We use it to create shared perspectives. That is what I think cubism is largely focusing on, showing that we don't use quantum mechanics in the same way. But then there's this question of these two are necessarily related via a kind of middle step, which is that theoretical intersubjectivity grounds intersubjective perception and communication, and that's what methodological intersubjectivity relies on. So I'm going to say some brief, very general remarks about perception, not going to get really deep into this field, but just to kind of illustrate what I think the definition of methodological intersubjectivity is useful for. So I think it's definitely uncontroversial to say that we do need perception and communication for methodological intersubjectivity to work. But it's important to note, and I think what hasn't been noticed in this field, is that measurement is not equivalent to perception. The measurement literature all agrees on this. Measurement is not the same as perception. So thinking about the examples I've been talking about, when I look at a clock, my clock is defined as running on international atomic time. It's not clear that I perceive international atomic time. I have to make quite a lot of inferences to understand that that's the phenomena that my clock is tracking. I have to relate it to these networks. I have to calibrate it. I have to apply corrections, uncertainties, and all of that. And this relates to kind of some of the early debates in relativity theory about the idea of, well, is the time that I subjectively experience the same as the time on the clock? It's not clear that there is an answer to that, because I have to decide what reference frame I take my clock to be situated in. I can approximate it incredibly locally to my specific reference frame, or I can approximate it to a shared reference frame of the kind of these Earth-centered, Earth-fixed coordinates. There is no theory-independent choice that I can make of that. So it's not clear what my perception is tracking. And finally, we could say, well, what is uncontroversial is that I do perceive a clock, and that if there's another agent in the room, I want to be sure that they are also perceiving a clock with the hands in the same position, regardless of what I interpret that to be. This kind of cuts out the stage of inference, but inference is where most of the intersubjectivity is created. It's how I infer what my phenomena is from the direct perception. So the question, which I think hasn't really been addressed very well, is does perception rely on theoretical intersubjectivity? It's not clear that it does, I think. People like Adlam, I think, argue yes, based on a basic assumption of physicalism, modeling, our conscious states are superimposed on a brain state of neurons, which are correlated to objects in the world. But I think this is massively underexplored. It's not making use of a kind of the extremely wide literature on the nature of perception. Perception lies well outside the domain of most physical theories, including quantum mechanics, even though agency and measurements are central to that theory. So why I think we need a definition of methodological intersubjectivity in this area is that it allows us to break down the steps in this debate into these kind of clear questions about how methodological intersubjectivity relies on perception. Does perception then rely on theoretical intersubjectivity? All of those are kind of open questions, which I think benefit from having clearer definitions of exactly what intersubjectivity is and how it functions within science. And that will help us answer the question of what exactly does a physical theory need to provide if it's to model the conditions for its own empirical confirmation. Okay, just briefly, here is a summary of basically everything I've said, in case you got lost in the details. So I've given this definition based on the coordination of perspectives and the creation of shared perspectives, which is really important to understand empirical confirmation. And I think the relationship between that and theoretical intersubjectivity is far more complex than is often given credit. Okay, thank you for listening.
I'll take a 2-minute break and then we'll have plenty of time for questions.